So today we're going to go over the solutions to the second practice exam. First, we're going to differentiate these two functions. To differentiate these two functions requires use of the product rule. So here we differentiate x plus 3 squared times x squared plus 2x minus 1 cubed. The derivative of x plus 3 squared is 2 parentheses x plus 3 times x squared plus 2x minus 1 in parentheses cubed. Plus, now we differentiate the first factor, 3 times x plus 3 squared. And to differentiate the second factor, we use the generalized product rule. The derivative of x squared plus 2x minus 1 is 3 x squared plus 2x minus 1 squared times the derivative of the inside function, which is 2x plus 2. Moving on to the derivative of x times 5x minus 1 to the 10th power. The derivative of x is just 1, so it's 1 times 5x minus 1 to the 10th. Next, we leave the first factor alone, differentiate the second factor. That again requires use of the generalized power rule. So bring 10 down, 10x times 5x minus 1 to the 9th times the derivative of the inside function. The derivative of 5x minus 1 is just 5. And then we're left with 5x minus 1 to the 10th plus 10 times 5 is 50, so 50x times 5x minus 1 to the 9th. Now, the next thing here, to differentiate this, we need to make use of the product rule and the generalized power rule. So the derivative of x squared minus, so we're going to rewrite this first as x squared times x minus 1 to the 7th to the 1/2 power. So remember, anything raised to the power, its derivative is going to bring down the power, replace the power with the power minus 1, and then multiply by the derivative of what was being raised to the power. So we bring down 1/2, we leave the inside alone, we raise it to the, it should have been minus 1/2, and then we multiply 2x times x minus 1 to the 7th, the derivative of the first factor, times the second factor, plus the derivative of the second factor times the first factor. The second factor here is 7x, 7 parentheses x minus 1 to the 7th. So that's why we end up with 7x squared times x minus 1 to the 6th power. Okay, now here we're using the quotient rule. So we're going to rewrite this as x squared over x minus 1 to the 1/2. The quotient rule says the derivative of the quotient is the derivative of the numerator times the denominator minus the numerator times the derivative of the denominator. The derivative of the numerator is 2x. We leave the denominator alone, x minus 1 to the 1/2. We subtract the derivative of the denominator, 1/2, times the numerator, x squared, times x minus 1 to the negative 1/2. So we get 2x times x minus 1 to the 1/2, minus 1/2 times x squared times x minus 1 to the negative 1/2. If we divide by x minus 1 to the 1/2 squared, we just get x minus 1. So that's because squaring undoes square roots. Okay, moving on to the second problem. So here it's very similar. Now we're just going to add the problem of finding the equation of a tangent line to a function, graph of a function at a given point. So here we find the equation of the tangent line to the graph of x plus 1 over x minus 1 at the point 2, 3. So again, the derivative of this function is the derivative of the numerator and times the denominator. Here the derivative of the numerator is 1, the derivative of the denominator is also 1. So the derivative of the numerator, 1 times the denominator, x minus 1, so just left with x minus 1, minus the numerator, which is just x plus 1 times the derivative of the denominator, which is 1 times anything is itself. We're left with x minus 1 minus parentheses x plus 1, so we're left with negative 1 minus 1, which is negative 2, all over x minus 1 in parentheses squared. So we're left with negative 2 over x minus 1 squared. Notice when x is 2, y prime is negative 2 over 2 minus 1 in parentheses squared. We're just plugging in x equal to 2 to this formula here. So what's 2 minus 1? It's 1. What's 1 squared? It's 1. So we're left with negative 2 over 1 squared. We get negative 2. This means the slope of the tangent line is negative 2. If we plug this into the point slope formula, here's what we get. Y minus 3, y minus the y coordinate, is negative 2 times x minus the x coordinate. Y minus 3 times negative 2 times x minus 2. And we can solve for y. You get y is negative 2x plus 7. Okay, it's the same thing here. Let's find the equation to the graph, equation of the tangent line to the graph of square root of x plus 7 over x plus 1 and x equal to 2. So notice here the y coordinate is not given. We can find it though just for plugging in x equal to 2 into the function. We get square root of 2 plus 7 is square root of 9, which is 3, over 2 plus 1. 2 plus 1 is 3. 3 over 3 is 1. So this tangent line has to pass through this point, 2, 1. Now, to find the equation of the tangent line, we have a point, we just need a slope. So to get the slope, we differentiate the function. We first rewrite the numerator, instead of square root, we write it as the 1/2 power, so we can differentiate using power rule. Root of x plus 7 to the 1/2 is 1/2 x plus 7 to the negative 1/2 times x plus 1, that's the denominator, so this is the dirt of the numerator, times the denominator minus the numerator. The denominator is just 1. Right? Dirt of x is 1, dirt of 1 is 0. 1 plus 0 is 0. And of course, we divide by the denominator squared. Next step, we just have to plug in x equal to 1. What do we get? 1/2 times 1 over square root of 2 plus 7 times, okay, that actually should have been, that should have been 1 plus 1, which is just 2. So this should have been, okay, I'm sorry, there was a slight error there. That should have been 1, that's 1/2 times 1 over 3 times, this should have just been 1 plus 1, which is 2. So this actually should just be 9. Should be 9 minus 3, which is 6, over 9. So this should have been 6 ninths, which should have been, so this is incorrect. I'll update that shortly. This should have been, so 6 ninths is the same as 2/3, so this should be y minus 1 is equal to 2/3 times x minus 2. Same thing here, again, it's the quotient rule. Y is 2x squared plus x minus 1 over x plus 1. Differentiate, we get 4x plus 1 times x plus 1 minus 2x squared plus x minus 1 times, okay, this actually should be 1. So when the derivative of x plus 1 is just 1, so this should be, so this is slightly inaccurate, that actually should just be, yeah, okay, so this, when x is 1, we get 4 times 1 plus 4 times 1, which is 4, plus 1, which is 5, times 1 plus 1, which is 2, so it's 5 times 2, which is 10, minus this thing, 2 times 1 squared plus 1 minus 1, so we get 10 minus 2 plus 1, which is 3, minus 1, that's 2, 10 minus 2 is 8, 8 over 4 is 2. Slope is 2, plug it back into point slope formula, y minus 1 is 2, parentheses x minus 1, or y is 2x minus 2 plus 1, 2x minus 1. Okay, last equation of the tangent line we're going to find, equation of the tangent line to the graph of x minus 1 times square root of x plus 3 at x equal to 1. So here, when x is 1, plug it in, we get 0. And then we just differentiate this using the product rule. Derivative of the first factor is 1. So we get x plus 3 over 1/2. Plus, now we leave the, so again, this was a slight error. It's 1/2 times x plus 3 to the negative 1/2 times x minus 1. Plug in x equal to 1, we get 1 plus 3 over 1/2, that's just 4, square root of 4, which is 2. And this, of course, is just 0, because 1 minus 1 is 0, 0 times negative is 0, so we get 2. Slope of the tangent line is 2. Plugging into point slope, we get y minus 0 is 2 parentheses x minus 2, or y is 2x minus 2. Now, the next 3 problems actually are about finding, given a function and graphing it, finding intervals of increase, decrease, intervals from cavity, local max and min, and then using all the including all the information on the graph. So let's look at this. State the intervals on which f of x is increasing or decreasing. So we differentiate this. We get 6x times x squared plus 1 squared. That's using the generalized power rule. We set it equal to 0. We see, okay, 6x, so that could be 0 if x is 0. x squared plus 1 is always positive. So if you square it, it's also going to be positive. This is never 0. So the only way this derivative is going to be 0 is if x is 0. X0 divides into two intervals, negative infinity to 0 and 0 to infinity. It's two subintervals. If we plug in any number that's less than 0 to f prime, we get a negative number. If we plug in any number to 0 to infinity, we get to f prime, we get a positive number. So we conclude f is increasing on 0 to infinity, and it's decreasing on negative infinity to 0. Okay, concave up and concave down, just differentiate again. We differentiate again using the dot product rule. So you can check this over. When everything's factored out, you get 6 parentheses x squared plus 1 times 3, 13x squared plus 1. So just derivative of first factor is 6 times the second factor plus first factor times the second factor. And again, that was using generalized power rule. X squared plus 1 appears as a common factor. When you factor it out, you get this 6 parentheses x squared plus 1 times x squared plus 1 plus 12x squared plus 1. Combine like terms, x squared plus 12x squared is 13x squared. You're adding 1. So we're left with this. And notice both these factors are positive. So f double prime is always positive, meaning the function is concave up on the interval from minus infinity to positive. And then the last problem, which is the graphic. So it actually looks like this. It looks kind of like a parabola. It's always positive, and it's always concave up, but it does change from decreasing to increasing at x equal to 0. I didn't ask a question here, though, but if I did, you can see it does have a local minimum at x equal to 0, or equivalently, actually, x equal to 0. 0, 1 has not just a local minimum, but an absolute minimum. Okay, now let's go down to function x cubed plus 3x squared minus 9x plus 5. We're going to determine the intervals on which f of x is increasing and the intervals on which it's decreasing. So again, we differentiate, factor, we get these critical numbers, negative 3 and 1. We have three subintervals now, negative 3, infinity to negative 3, negative 3 to 1, 1 to infinity. So if you plug in any number from minus infinity to minus 3, and plug it in here, the first factor is always positive, it's 3. The second factor here is going to be negative. The second factor is also going to be negative. Negative times a negative is positive, so that means f prime is positive. F is increasing on negative infinity to negative 3. If we look from negative 3 to 1, say x equal to 0, first factor is positive again, second factor is positive, but now third factor is negative. Positive times negative is negative. So that means f prime is negative, or f is decreasing on the interval from minus 3 to 1. If x is in the interval from 1 to infinity, first factor again is positive, second factor is positive, let's say x is 2. And now third factor is also positive, positive times positive times positive is positive. So again, f is increasing. Okay, to determine whether it's concave up and concave down, just differentiate again. You get 6x plus 6. You can check that. And this should be familiar by now. The second percent of the second derivative equal to 0. We get 6x plus 6 is 0, or x is negative 1. X equal to negative 1 divides the real number line into two subintervals, negative infinity, negative 1 to infinity. If you plug in your favorite number that's less than negative 1, say negative 2, 6x plus 6 is going to be negative. You plug your favorite number that's larger than negative 1, let's say 0, to 6x plus 6, you get a positive number. We can conclude f is concave down, negative infinity, negative 1. It's concave up, from negative 1 to infinity. Now, we can just, from the information we saw in parts A and B, we can determine the x-coordinates of inflection points. So f changes from increasing to decreasing at x equal to negative 3. F has a local maximum at x equal to negative 3. Since it changes from decreasing to increasing at x equal to 1, and f has a local minimum at x equal to 1. Also, from part B, we see f has an inflection point since it changes from concave down to concave up at x equal to negative 1, has an inflection point at x equal to negative 1. And here's a graph. So all these coordinates were labeled. You see here, okay, it starts minus infinity, it goes all the way up, it's increasing to its local maximum, and starts to decrease. Now, so all here, it's concave down, right? It's concave down from negative infinity to negative 1. And now, so that's where we have inflection point. Now it changes So it changes from a frowny face to a smiley face, and it changes from being concave down to concave up. So now the function is concave up on the interval from -1 to infinity. When x is equal to +1, it has a local minimum. Okay, so that's the graph. All those points are included. And again, it's not super important. You don't have to say, don't worry about the exact y value. We just care about making sure the x value of the local minimum is accurate, the x value of the inflection point is accurate, and x value of the local maximum is accurate. The fact that this is -3, 32 isn't that important. What is important, though, is that the x-coordinate is equal to -3. That's what should be on the graph. Okay, so the last function we're going to graph is tan squared of x minus x. We differentiate this, we get 5x to the -1/2 minus 1. Critical number is 25. Now notice this is only defined because you can only put in a positive number to the square root function. It's only defined when x is larger than 25. I'm sorry, when x is larger than 0, larger than or equal to 0. So x cannot be negative, we put again. So that's why we divide up not just the real number line, but the half real number line, that is the portion of the number line from 0 to infinity, positive numbers, and we divide it up at x equal to 25. So from 0 to 25, when you plug in f prime, it's increasing because plug in your favorite number. Let's notice when x is, say it's 1, 5 times 1 is 5, minus 1 is 4, that's positive. But if x is large, let's say 36, then so what is this root? This is 5 over square root of x, right? 5 over square root of x minus 1. When the square root of x is small, or x is small, this is going to be larger than 1, but when x is large, let's say x is larger than 25, this is going to be less than 1. So something less than 1 minus 1 is going to be negative. That's why f is increasing on the interval from 0 to 25, and it's decreasing on the interval from 25 to infinity. Okay, now let's determine the intervals on which f is concave up and concave down. So here, we just differentiate it again. We get this, -5/2 x to the -3/2. Now notice x, so the function's only defined for x larger than or equal to 0. So we really don't care about what happens if we're going to get an interval concavity. It's going to have to be in the interval from 0 to infinity in the first place. So let's just restrict ourselves now for x being larger than 0, and we see this is always negative, right? X to the -3/2 is positive because x is positive. -5/2 is negative. A negative number times a positive number is a negative number. So we see it's concave down on the interval from 0 to infinity. And now we can just read off, okay, so because it changes from increasing to decreasing at 25, it has a local maximum at x equal to 25. There's no inflection point because it doesn't change from concave up to concave down. It's always concave down on the whole interval where it's defined. Okay, and here's the graph. So you see here, here's graph local maximum point. Again, what's important is you specify the local maximum occurs when x is equal to 25 and draw a function that is first increasing concave down until 25. So it has the shape of, so this always has the shape of a frown, but it starts out increasing. A frown starts out increasing, reaches the maximum, and starts out decreasing. Equivalently a hill, so it has the shape of a hill. Reaches the maximum, and then it ends up decreasing. As the hill sort of spread out because it's the square root function. Okay, now we just have 2 more problems. So here we have a rectangular garden that consists of 4 pieces of fencing. It's to enclose 100 square meters. Our job is to find the dimensions of the garden that will minimize the amount of fencing used. So if we let L be the length of the garden, W be the width, the area of the garden is L times W, which is 100. We can solve for W in terms of L. W is 100 over L. The amount of fencing used is equal to the perimeter of the garden. So that's just 2 times the length plus 2 times the width, or 2 times L plus 200 over L. And so perimeter is now a function of L because the restriction on the area, setting the area equal to 100 square meters, meant that